This presentation is on nuclear charge, and we're going to figure out what nuclear charge is and then what its effect on the various periodic trends will be, both across the table and down the table. All right, so to look at the periodic, the trend for nuclear charge across a period, so across a row, we're going to first look at a model for lithium. And lithium has, it has 3 protons and it has 4 neutrons in the center. Okay, and then as a result, it has 3 electrons, and we know that there are 2 electrons in the first shell, and then we have 1 electron in the outer shell. All right, so we have 3 electrons there. When we go to, when we look at the effect of the nucleus as a whole, so this entire bunch of particles in the center, we have 3 positives hanging out in the center. And those positives are going to attempt to attract these electrons, these negative electrons, as they orbit around the nucleus. And what you need to think about is that the nucleus has a power of 3, and it has the pull, because positives and negatives are oppositely charged and they will attract each other, but the pull to these each electrons has a power or a charge of 3, so it has, well, we could assign this a pull of 3. Okay, and if you look at, for instance, the next element, beryllium, we were going to go ahead and draw in beryllium, and beryllium has 4 protons, 4 pluses, and it has 5 neutrons, and in its outer shell it has 4 electrons. So we have gained 1 more electron and 1 more proton, which is what you get whenever you move to the next element. You gain an electron and a proton at minimum. You also gain neutrons, but we're not really worried about them right now. So as we move to the next element over, and we have boron now, our pull from the center is now a power of 4. So each electron is experiencing, the nucleus power has increased. We could call it, it has a magnitude of 4 now. So what happens is, as we move across a row, you have an increase in nuclear charge. Now sometimes this is going to cause our trends, as we learn, our trends may cause the electrons to get pulled in just a little bit more. As you can see, we could imagine here, our electrons would be pulled in just a little bit more, so they would be closer than the electrons in the lithium in the second energy level, because there is just a little bit more charge. Now you may not see as much difference here in the first 2, but as you work across the periodic table and you get to the 8th row, you're going to have a difference of 8 electrons as opposed to, 8 protons as opposed to 1 proton. So you can see, as you increase the number of protons in the center, the attraction or the pull on each electron is just a little bit more. And as you stay in the same energy level, so we're going to be, each additional electron that we would add would be here in the same energy level, it's going to have an increasingly bigger pull toward the nucleus. Down a column is much more easy to recognize the effect, or down a group. You can also call it a family. The electrons that you're adding here right now would be in the outer row. And so you can see that the nuclear charge is going to have the same pull for anything. So we'll say this is our nuclear charge. We're going to have the same pull here on any of these electrons. They're all on the same energy level. But whenever you take your mass of your nucleus and you now add your electrons in a new row, you're getting further away. And so the pull is, or the pull towards the nucleus is just a little bit less because you have gained another energy level, and you have the electrons that you're being adding to this element are further away. So that is the two effects of nuclear charge, both down a group and across a period.